Hi everyone, this is Anna Bergstrom and we are moving through the acid-base chemistry and carbonate system module, and today we are actually going to dive into the carbonate system and also talk about this interesting principle called La Chatelier's principle. So by the end of this video, you should be able to do a bunch of things. First is, given a reaction, determine which direction it will shift to attain a new equilibrium. The other thing is to write the equations of the carbonate system. Given a pH, determine the relative prevalence of each species in the carbonate system, and explain how La Chateliers applies to the carbonate system. Okay, so before we dive into the carbonate system, first, what is this La Chateliers stuff? So, of course, surprise, surprise, it is another white man from the history books, this time of the French variety. He studied at La Sorbonne and did a bunch of fun chemistry and came up with this principle. So this principle is that when any system at equilibrium for a long period of time is subjected to a change in concentration, volume, temperature, or pressure, a couple things are going to happen. First, the system changes to a new equilibrium, and second, this change partly counteracts the applied change. So, very simple example. If we were given this equation, A plus 2B yields C plus D, what would happen if we added more of A? Well, I'm pretty sure you guys probably know at this point that if you added more A here, the reaction would shift towards the products, because you need to generate more products to counterbalance the increase in the reactants that you had. Similarly, if you decrease the concentration of A, you would shift the reaction in the other direction, because again, we need to move more into the product side to compensate for that loss of products. So I think you'll realize at this point you probably already knew La Chatelier's example, you probably just didn't know the name of it. So that's a really simple case of applying La Chatelier's to an equation. But one place that La Chatelier's principle is working really hard is in the carbonate system. And in this classic example of the carbonate system is ocean acidification in our really fun world of climate change. So first we're going to talk about the carbonate system, and then we'll come back to the ocean with new knowledge to understand how that's working. So to kick this whole thing off, we need to start by thinking about the dissolution of CO2 in water. So if we have some air-water interface where we have air above water, and we know that we have quite a bit of CO2 in our atmosphere as a gas, we also know that we can have CO2 in our water in dissolved form. And what happens is we have molecules of CO2 moving into the water and molecules of CO2 moving back into the air. And if we have some fixed partial pressure of CO2 in the air, eventually we're going to reach an equilibrium between the amount of CO2 we have in gaseous form in the atmosphere and the amount of CO2 we have dissolved into our water. So once we get CO2 into the water, we can start really rolling here. So the next thing we do is we take that carbon dioxide and we hydrate it. So the equation for this is CO2 in aqueous form, just beautiful handwriting, plus water yields H2CO3. And this, by the way, is carbonic acid. Okay, and as we've had with everything, we know that we have a bunch of equilibrium constants. So in this case, again, H2O is just H2O. How we write out our equilibrium constant for this is our products on top, so our carbonic acid on top, and our CO2 on the bottom. And the equilibrium constant for this is about, well, it is at standard temperature and pressure, 10 to the negative 2.8. So one thing to note about this, you remember really the driving force here is the amount of CO2 that we have. because we need CO2 in our water in order to move along this and hydrate that CO2 into carbonic acid. So really this is a function of the partial pressure of CO2 in the atmosphere overlying whatever body of water we're interested in. The other thing to note here is at low pH, it's going to be slow to attain equilibrium, which that low pH is about pH of 10. So typically there's organisms living in whatever fluid, or the human body, for example, does this, is it biologically catalyzes the hydration of CO2. So it's pulling CO2 into whatever fluid we're interested in and moving it along this carbonate equilibrium and kind of attaining the equilibrium artificially faster than it would on its own. The other thing to notice is that this carbonic acid is a weak acid, and typically really what we're talking about actually is just CO2 dissolved in water. So you'll see it frequently written as H2CO3, sorry guys, H2CO3 star, which is actually the combination of aqueous CO2 and carbonic acid itself. Okay. Yeah, so typically you'll see it referred to as carbonic acid or carbonic acid with this little asterisk, and know that it actually means the combination of CO2 dissolved in the water and carbonic acid. Okay, so we've hydrated our carbon dioxide, now we can move along the carbonate equilibrium. So the next thing we do is dissociate our carbonic acid. So that happens in two steps. We have H2CO3 going to bicarbonate, HCO3 minus, plus our proton. And our equilibrium constant for this is the concentration of protons in solution plus the concentration of bicarbonate all over our concentration of carbonic acid, or CO2. And this equilibrium constant is 10 to the negative 6.4. Okay, so that's the first step, so you'll frequently see this denoted as K1. The second step is taking our bicarbonate and dissociating it further, taking off that other proton and turning it into carbonate and yet another proton. And so our equilibrium constant for this, which you'll see as K2, is the concentration of protons in solution plus, oops, gotta get that back, plus the concentration of carbonate in solution all over the concentration of our bicarbonate. And this equilibrium constant is 1 times 10 to the negative 10.3. Okay, so those are how we go from carbonic acid to bicarbonate to carbonate, and we're donating protons as we go. So at very high pH, pH is greater than about 11, we have a high concentration of hydroxide ions floating in solution. And so if we have a lot of hydroxide ions floating in solution, we end up just going from aqueous CO2 straight to bicarbonate. So that's just something to keep in mind. That's working at super high pH. and that is a pH greater than 11. Okay, so now we've gone through the whole steps of going from CO2 into carbonate, and now we want to look at how that actually works over the range of pHs here. So this is a classic diagram that you will see. We have pH on the x-axis and the molar fraction of dissolved inorganic carbon, and by that it's just all of these species of carbon, so carbonic acid, bicarbonate, carbonate, that is dissolved in water, and it is inorganic. So our molar fraction of DIC. So here at low pH we have a lot of this dissolved carbon dioxide and carbonic acid, or we can also call this H2CO3 with an asterisk. Then as we increase our pH, our protons are going to start coming off of our carbonic acid to be the to counterbalance the increase in hydroxide ions. So we are going to move into a system that is more dominated by bicarbonate. So our molar fraction of bicarbonate is increasing as we slide along this pH scale. And then if we keep going into even higher pHs here, we are going to keep plucking off protons, and we'll end up with a system that is dominated by carbonate here. So at that point we have no carbonic acid, you'll see, and our relative proportion of bicarbonate is declining, and our amount of carbonate is increasing. So this diagram you'll see a lot, but one thing that you need to know about it is assuming a fixed total carbon. So we basically have a constant amount of CO2. We're in a closed system. We can't dissolve any more. We also can't precipitate out any of our carbonate. And so we have a fixed amount of carbon. This all sums up to 1 here at any point along your pH. But in the real world, we have this kind of infinite supply of CO2. So how this works in the real world actually looks a little bit different. And so this is if we have no limit to our available carbon, which basically means we can always pull more CO2 out of the atmosphere and dissolve it into our liquid. So that is why let me back up for a second. We are, say, for this figure, working at 0.035%, which is also 350 ppm of carbon dioxide, which now we are well above 400 ppm in our world today, but you'll see a lot of these figures back when we had a lower amount of CO2 in our atmosphere. So this is, again, we have pH on the x-axis, and this is our log of our concentration of dissolved inorganic carbon species on our y-axis. And because our liquid and our atmosphere come into equilibrium, and we have a fixed amount of carbonic acid. In this case, we're calling it H2CO3 star, so carbonic acid, which is also that plus our dissolved CO2. So we have this fixed total amount no matter what the pH is, because if we pluck some carbonic acid and move it along our carbonate system, we're just going to pull more out of the atmosphere and move it into solution to compensate for that. So it's in equilibrium between the fluid and the atmosphere. So at low pH, all anything ever is this carbonic acid. As soon as we get to a pH just a little greater than 5, we're going to start dissociating those protons off of that carbonic acid and turn it into bicarbonate. So this line right here, oops, it's already labeled, is bicarbonate. So we will start increasing our concentration of bicarbonate, and that's just going to keep increasing. As soon as we get to just below a pH of 8, we're going to further dissociate the bicarbonate and start creating carbonate. And that is just going to start increasing. So here is our K1, where we're start our bicarbonate is in equilibrium with our carbonic acid, and here's our K2 where we start plucking out our carbonate and our second equilibrium constant. So again, because we have no limit to the total available carbon, we're just going to keep creating our bicarbonate and our carbonate, and we're going to keep pulling CO2 out of the atmosphere. So coming back to our example of the ocean and thinking about, now that we have a little bit better understanding of the carbonate system, we can think about what's going on in the ocean and using Le Chatelier's principle. So you'll know that our CO2 in our atmosphere is increasing. So because we've created anthropogenic CO2, the overall CO2 of our atmosphere is increasing. So this flux between our ocean and our atmosphere, we're forcing more into the ocean. And if we put more into the ocean, we're effectively creating more carbonic acid. So that carbonic acid is going to dissociate into two protons, it's going to create two protons and some carbonate, and that results in a pH decline, again, because we're increasing our concentration of protons here. So if we do that, we are creating this acidification process here. And so this is how Le Chatelier's comes into play. If we have more reactants, more CO2 in the atmosphere, we're going to have to shift in this direction along the carbonate system to account for that. And we've created this giant backup of carbonic acid. We've decreased the pH here. And if we do this, we result in undersaturation of our bicarbonate here. And that means that there is not enough available. It's shifted back along the carbonate system, and we are causing huge issues for those marine organisms that rely on the ability to have carbonate around to build those shells. So any shelled creature, diatoms, coral, all of those are sort of essentially being dissolved by the new, more acidic water. That more acidic water needs to go somewhere, so it's taking the carbonate out of the hands of the shelled creatures and using it, according to Le Chatelier's principle, to balance out this system. So one last thing, some kind of fun aside, is carbonate reactions at work in space. So when they initially designed the International Space Station, they were using an atmospheric CO2 concentration of what you'd expect on Earth, right? So around a little over 400 ppm at this point. And then they put it up into space, and because there's humans living and breathing CO2, and it's in that way kind of a closed system, they probably weren't able to scrub enough CO2, so that caused an increased CO2 concentration above the environmental conditions it was designed for on board the International Space Station. So the tubing for the cooling system was Teflon tubing, which is you can have atmospheric exchange between the air in the International Space Station and the fluid that was in that cooling system. So CO2 was dissolving across, that increased concentration of CO2 was causing CO2 to dissolve across that Teflon tubing barrier into the fluid in the onboard cooling system. Just like the ocean, it was decreasing the pH because we had more carbonic acid. Those protons were dissociating, were causing a lower pH there. And so that brought down the pH to a place where it was corroding the hardware on the onboard cooling system, which was causing huge problems and potential health and safety risks. So they panicked a little bit, and then they calmed down and figured out that if they just increased the pH, And again, using Le Chatelier's principle, if they shift the pH so it's back where it needs to be, they can kind of compensate for that and allow some of the carbonate to complex with magnesium and sort of precipitate out of the cooling system and keep everything hunky-dory. So that is two different applications of Le Chatelier's and the carbonate system in space and in the ocean. So I hope you guys got something from this lecture, and we will pick it back up in the next one.